L07-2 and as I increase the force, the sample will deform. And it will deform more or less like this. First it will be a little bit soft, then it will go through a linear section. And do you think we can load the rock forever? The force can increase forever for this particular rock. There's going to be a limit, and that's how much force a rock can take. And it will go through a peak, and then it will break. We're not going to talk about the peak right now. We're just going to say that this value without confinement is called UCS, and that stands for unconfined compression strength. We'll talk a lot more about that later on. But for now, I'm interested in the slope of this linear region, and this is, if this is equal to 1, this is going to be the Young modulus. Because it's going to be the difference in axial stress divided the difference in axial strength. Something that we are not going to do in class because we don't have the tools to do it in this example, but you will have to do in the homework. And that's the first problem, is you also have to measure the Poisson ratio. We cannot do this in here, but I can do it in my laboratory downstairs. So I gave you the data for a shale sample I tested some time ago. And we're also going to measure radial strain in that case. And in the radial strain, it's going to have a negative sign because it's going to expand, and this is going to look more or less something like this. And it's going to go also to a peak, and it will do something like that. So, again, this is for the axial strain. This is from the radial strain. From this same region where you compute the Young modulus, you can also get the change in radial strain. And notice that the change in radial strain is going to be smaller than the change in axial strain. The ratio of that is going to give you the Poisson ratio. Okay? So, for the given, the same segment, this is the difference in radial strain. And in this case, I say this is equal to 1, but in general, this is going to be equal to the difference in axial strain. And when you divide those two according to this equation, you get the Poisson ratio. Okay, so let's see how this works, and actually we're going to do the test right now. We'll see how many samples we can do. Okay, so let me try to see how it's going to be helping you with the laboratory. So for this week and next week, we're going to do it here, but later on, see how it's going to help you in the laboratory downstairs. And he's going to take attendance too, right? Are you taking attendance?
I printed because the front desk told me they do not receive your email. They don't receive anything. I printed the student's name.
Okay. So while I run the experiment, you take attendance, okay? Just go check in every row. Okay. So guys, so this is a machine. This is a load frame that you're going to use in the laboratory. And basically, what we do here is by moving up this plate and reacting against this frame, we apply a compression, okay? And here we have some samples. We'll see how many we failed today. So all these are Berea sandstone samples. And we're going to load them, put them in here, and see how the force increases. I'm gonna need people to help me out. Who wants to help me? I need someone to help me here with the computer, and I need some other one to help me operate the low frame. What do you want to do?
I'll
You'll break the rock? Okay, but you have to be careful. Okay, well, okay, come on in. And who else wants to help me? Okay, okay. Then you come here and operate the computer. Okay, so I'm going to start the software here. By the way, I uploaded in Canvas the manual for the labs, so you can take a look at that. And I think this should be already okay. Let's first set up this. First of all, what we have to do is we need to get the top of the reaction frame here close to the rock. So the frame has two operation modes, one fast and one slow. If you just press like up and you keep it pressing, it's going to go fast. But you do this only when the sample is not in the air, and also when this thing is not engaged to the displacement transducers. This is a device that measures displacement and measures like up to 0.01 inches, something like that. All right, let me see. It's quite far. Can you help me out? What's your name?
Daniel.
Daniel? Okay, just press up and keep it.
Until you say no?
Yeah. And then I'll tell you stop, okay? So, again, you only do this when there is nothing in there. Just keep on going, and actually, okay, stop, okay. So now I'm gonna put the sample here, and it's barely below this screw. Let me see if I can move the screw a little bit. No, actually it's quite stiff, but that doesn't matter. It's barely touching. I place it in the center, and what is the load? What do you read here?
Negative 26 pounds.
Okay, you guys take notes, okay? Because you have to then later use this data to run the experiment. Negative 26, that actually means 0, okay? So when you read your data and you read the negative 26, that's actually 0. Okay, so what we're going to do now is we're going to change here the speed, and we're going to adopt 0.002 inches per minute, okay? Mm-hmm. So let me see if I remember how to do this. So digit, just press digit. Mm-hmm. One more time, and then up, and that's going to change it to 0.02 inches per minute. So what that means is that we're going to move this plate at a velocity of 0.02 inches per minute, okay? That's going to be very important because in our test over there, what is going to be a constant is what is called the strain rate. The strain rate is going to be 0.02 divided, this sample is about 2 inches. So 0.02 divided by 2 is going to be 0.01 strains per minute, okay? All right, so I think this is in the center, we're ready, and I'm going to press speed again. And okay, we're ready. The next thing we have to do, but don't do it now, is just press up, okay? And before we do that, we forgot the most important thing. First of all, is the shield, but also your safety glasses, and my safety glasses. Okay. So, fancy safety glasses.
So when you're pressing the button,
yeah.
So I cannot just keep pressing it. I have to do it sequentially.
No. Just once.
Okay.
Because now when you press up, it's going to move at that velocity that we told. All right, you ready?
Yes.
Okay. So you're going to have to tell us what's going on in here. So here, load cell you're gonna have to hit start, and start is gonna start recording, okay? And after this starts recording, you're gonna start seeing values here.
Okay.
So I like that you tell us, when the low cell gets to 100 pounds, just tell us, 100 pounds, 200 pounds, so on, okay? Just to tell everyone what's going on, because from far away you're not going to be able to see. All right, there's one more thing I have to do. I have to, can you do cameraman too, just for a minute? In order to measure displacement, I need to see how the plate moves in relative to this. So I need to use this platform, and I have to make it barely touch that sensor, and I think now it's ready. So okay, you hit start.
No.
Yes. All right, that's good. That beep is good. And now, okay, what do you read here?
-13, -14.
Okay, that's the force, okay, in the computer. But again, that's 0. And what is the displacement here? Displacement number 2?
0.04.
1 and 4, okay. So, we're gonna do the following. And you're gonna press up, and when it gets to 1,000 pounds, you're gonna press down. When it gets to 500 pounds, you press up again.
Okay, so when I press up,
Just
do I
once.
wait until he says the result?
Okay, you can also see here. Don't worry. Okay, just press up.
Yep.
And all right, what's going on now? This moving, right? Displacement 2 is moving, but since there is a very small gap, the frame still didn't touch the rock. But once it touches it, the force is going to start to increase very quickly, which is now it's barely touching, but soon it's gonna.
Yeah, now it's positive.
Okay, now it got positive over there. So this one is moving up very slowly, and this one is starting to pick up a load. And what do you measure now?
It's 45.
Okay, tell us when you get to 100. No, just okay.
Just 100?
To 1,000. We'll get to 1,000.
Okay. 100?
100.
Okay, so already we have 100 pounds over here, all right?
It's going a lot faster.
It's going a lot faster because of that.
200.
Before it starts sort of flat, and then it goes quickly because we're setting the strain rate constant.
300.
Okay. So again, when it gets to 1,000, just press one time stop, okay?
400. 500.
Don't worry, you'll be fine.
600. 700. 800.
Okay.
900.
Okay, stop. All right. Now,
1,000.
this one is not moving anymore, and the force it's about constant. It's going down a little bit, and we'll explain why later on that the force is going down. But what's the value right now?
1,000 flat, like 1,002.
1,002?
Yeah.
Okay, but I'm sure it's going to go down just a little bit. It's going down here. You see, Daniel, right?
Yeah, the machine
Okay.
reads 987.
Yeah, it went down like 5 pounds. Okay, so I want to warn you guys. This may do a very loud sound, okay? So don't be scared, it's fine. It might be loud, it depends on the type of rock, but don't be scared, that's gonna be fine. So now press down.
Okay, just once.
Yeah. Okay, now we are unloading. When it gets to 500, go stop, okay?
Okay.
We're doing this step of unloading because we also want to measure something which is called, that's fine, the unloading Young modulus, which is not going to be the same as the loading. Loading and unloading, that's going to be different. And I'll explain why that later on. And now let's go loading again. Up.
Down? Up.
Yeah.
Up to.
Yeah. Up. Let's go to 3,000. Let's see if we get to 3,000. Okay. So now I'm going to get a little bit closer to here.
900, 1,000, 1,100.
Okay.
1,500.
Okay, guys, we have about 2,000 pounds now on the road. There's no break. Okay?
Yeah, 2,000.
What is the weight of a longhorn? 2,000 pounds. So we have a longhorn stepping on that rock and it doesn't break.
2,500.
Okay, we'll get to 3,000, then you will stop it.
2,800.
And we'll do again,
Yep.
unload,
3,022.
Down?
unload, yes, to 500,
Okay.
to 2,500.
Okay. Right now?
Yep. Let's go a little bit more. Actually, let's go to 2,000
Okay.
because this is a little bit fast. So I'm worried that we don't have enough data to measure that. So, okay, stop. And then go up again.
Up to,
Yeah. Up to, let's say 6,000.
oh, okay.
We'll see if it gets to 6,000. Okay, again, Daniel, can you see any strain in the rock? Can you see that it deformed?
I have a little chip rock, but I don't see any
Okay.
deformation.
Yeah, that little chip might have been caused because of some irregularity on the face of the. But just come this, Daniel, stand up, please, because the shield is
Okay.
just on this side. But I mean, but you don't see that. Oh. Okay. Okay. All right. So that was the sound that I was telling you about. Now we're gonna stop it. You're fine.
Did I press stop here?
Okay.
You didn't tell me it's gonna.
Okay. So I told you to stay here, right?
Yeah, you're very smart.
Yeah. Okay. What was the maximum load?
Maximum load here. Can we point it here?
Yeah. So it was about 3,600 pounds. Okay. So